right? Heat, and work, right? This is exactly where we knew we were going with this, right? Because we have to be able to measure things. If the whole point of energy is seeing why chemical reactions happen as they do, then we know we're going to be measuring these things as time goes on, right? So we're going to quantify this stuff and get some numbers out of it. All right, so first of all, it's important to appreciate that if heat goes into a system, you have a change in temperature. If heat goes into a system, you have a change in temperature. All right, now it turns out we're going to be able to measure this. How much does the temperature change? Well, it depends on the heat capacity of the system. Okay? So if we're going to put heat into a system and change its temperature, some systems have a great heat capacity. They can take a lot of heat and without changing the temperature a whole lot, and some can't. Okay? So that depends on the heat capacity of the substance. All right? I think we've got a table here. Yeah, so this is cool. Very cool. Look at this. Water has a heat capacity of 4.18. Wow, look at that. 4.18 joules per gram degree centigrade. That's amazing. 4.18 joules per gram degree centigrade. It's amazing when you think that lead and gold like are almost a 40th of that, right? Or a 30th of that. In other words, if you put, let's say, 2 gallons, let's give you a real unit. Let's say you put 2 joules into a gram of water, it raises the temperature by a certain amount. But look at that, you put 2 joules into a lead or gold, it's going to raise it up dramatically because these things have a very small heat capacity, right? Q is equal to C delta T, right? And so if this is small, that means this is going to be big for the same amount of heat that goes into it. Wow, that's really remarkable. Water is a lovely, lovely thing. Look at water compared to everything else on here. Okay, it has a huge capacity to take in or let off energy. It's a great reservoir for heat or for energy. Okay, so you notice that the units in the heat capacity table were in grams. Let's see, they were in joules per gram degree centigrade. And look at this. This is the reason why, because oftentimes when we're saying how much heat can a particular thing take, how much heat can a particular material take? Well, it depends on how much material you have there, right? And that's why we're concerned about this. Okay. So what are the units of mass? They're going to be grams, right? Let me change colors here. Grams, and these are going. What are the units of joules of heat going to be? Joules, right? And what are the units of temperature going to be? Kelvin or degrees centigrade. Agreed? So what are the units of heat capacity going to have to be? You know what you should do? You should pause the video and solve that. You can see that joules is going to be grams times this thing times kelvins or degrees centigrade, right? So what are the units of that going to be? Please pause the video and solve it. Okay, let me suppose you solved it. You see that joules are going to be on top, so joules are going to have, let me go back to red now. It's going to have to be joules because when everything cancels out, you have joules in the numerator over here, right? And there's no grams over here, so it must be grams below it. So grams are here, and they cross off with that. And there's no degree centigrade over here, right? So it's going to be degree centigrade. Those are going to cross off, right? So the units for, I'm going to call this heat capacity out of an old habit, but really this is the specific heat capacity. Specific heat capacity. And it's going to be impossible to get these guys mixed up if you're watching the units. Heat capacity and the specific heat capacity are identical, different only by mass. Okay, so watch out for the units, and you won't get that wrong. All right, so let's look at this. Suppose you find a copper penny in the snow. How much heat is absorbed by the penny? Heat. how much heat is absorbed by the penny as it warms from the temperature of the snow, which is -8. T1 is equal to -8 degrees centigrade, to the temperature of your body, T2, 37 degrees centigrade. So the change in temperature is going to be 45.0 degrees centigrade. Okay, now watch this. You may be concerned about using degrees centigrade instead of kelvins. Watch this. If I change this to kelvins, this is going to be 273 minus 8, which is going to be 265 kelvins, right? And 37 degrees centigrade. I can't do that in my head. What is 37 degrees centigrade in Kelvin? 37, 273. It's 310, I think, right? Yeah, 310. 310 Kelvin. And what's the difference between these two? 310 minus 265. Can you see it's 45? So when we're talking about differences, kelvins and degrees centigrade are the same, right? Because I guess I should ask you that. Why is that? All right. So if you're ever concerned and you don't know what to use, I think you'll find that if you're using in these ones degrees centigrade, you'll be fine. If you're careful about the units, when you're given these tables, you'll be given that unit, right? And just use degrees centigrade, you'll be fine. Okay. So, and final thing I'm supposed to see is assume the penny is pure copper and has a mass of 3.1 degrees centigrade. Mass 3.1. Oh, I said degrees centigrade. Sorry, 3.10 grams. Okay. So I look over here. Actually, you know what? This table is not given to you in the book. I put that there to make it easier. You have to know to go look for it, right? Or you can say to yourself, I know what the formula is I'm going to use. It's a workhorse formula. Q is equal to mc delta T. This is really specific heat capacity. The mass is 3.1 grams, right? And this is a penny, it's copper. So I come over here, it looks like it's 0.385 joules per gram degree centigrade, right? And this is 45.0 degrees centigrade. Can you see the degrees centigrades are going to cross off, the grams are going to cross off, and I'm going to be left with joules, which is exactly what I wanted. Now, it looks like it's 3.1. 3.1. How do you spell 1? 3.1 times 0.385 times 45. It looks like it's going to be 53.7075 equals 53.7075 joules. How many sig figs do I have here? I've got, that was 2 sig figs here, right? Well, actually, no, that one's gone. Yeah, that would have been 2.2, and this would have been 0.2 and 45. Okay, so it's 3 sig figs here. 3 sig figs here. I didn't write, I wrote 3.1, but it's really 3 sig figs if you look at the question, right? And this is 3 sig figs. Okay, so this is going to be 3 sig figs. So this is going to be about 53.7 joules is my answer. That's the heat. Where's the question? How much heat is absorbed by the penny? 53.7 degrees, or joules. Okay, 53.7. And when it says how much is absorbed, can you tell that that's really just going to be the magnitude of it, right? It wouldn't be negative or positive. It is positive, but I mean, it wouldn't be, we're not concerned about it's negative or positive because it says absorbed. Tro's not 100% consistent with that, but fortunately I am. Okay, let's do another one. Now, this is a very common way of measuring these kind of situations because you can imagine how easy it is to make a bath here where you've got some object in water. And suppose you've got this object at some temperature, let's say, I'm going to say hot, okay? Hot. And the water is cold, what's going to happen? Well, all the heat from the block of metal is going to go into the water, right? And so whatever heat that you lose here, you're going to gain here, and that's why one is positive and the other one's negative. If this is negative, can you see a negative of a negative is going to make that positive? Right, so it doesn't matter. The point is that they're opposite in sign, and that's a true statement, no matter which way you look at it. Okay, so thermal energy transfer, a 32.5 gram cube of aluminum initially at 40. All right, so this is in grams of water. You know what I'm going to do? I'm going to say, I get real confused if I don't write some tables out. You've seen me do that before. The mass, and I'm going to put this in grams. This is 32.5 grams of aluminum. Initially, T1, 45.8 degrees Celsius, is submerged in that much water at 15.4 degrees Celsius, and it's 105.3, right? What is the final temperature? This is a very common problem. All right, so what I'm going to do is I'm going to first of all look over here, and I'm going to see my specific heat of aluminum is 0.903, 0.903, and my specific heat of water is 4.18. 4.18, it's really 4.184, but to go to 3 sig figs is that. Here's what I know. I know that Q is equal to mc delta T over here, and Q is equal to mc delta T over here. And I know that whatever one gains, the other one loses, okay? So I'm going to put this one as negative because I can see that the temperature of the water is going to go down. So let's say if this is negative, then these two are going to equal each other, right? And so if that's negative, sorry, that's going to be negative 2, right? Also, can you see that? So what I'm going to say is that I'm going to get rid of that Q and that Q because it doesn't matter how much heat is being lost. It looks like mc delta T, this negative, is equal to mc delta T, this one, right? And this is mc T2 minus T1 is equal to mc T2 minus T1. It really helps that I've drawn this in columns, right? Because I won't lose which one is which. I know this C is 0.903, this C is 4.18, this M is 105.3, this M is 32.5, but this is really what I'm looking for, is T2. I'm looking for my final temperature of both of them. Agreed? All right, so now I'm going to say, I'm going to do a bunch of algebra here. This is, I don't have room for this, do I? I do not have room for this. This is mc T2 plus mc T1 is equal to mc T2 minus mc T1. This T is different than that T. What I'm going to do is I'm going to underline everything that's in aluminum, okay? That's aluminum, that's aluminum, that's aluminum, that's aluminum, and that's aluminum. And this is water, this is water, that's water, that's water, and that's water, okay? Now, I gotta get my T2 terms on the same side, and I've run out of space. But I'm gonna change colors here, and I'm gonna come up here, and I'm gonna rewrite. I'm gonna come up here to my next line, and I'm gonna write real small. You're gonna have to either blow this up or do it in your on a piece of paper, and just hope that what you can't see is the same thing as. You need to solve this. I don't think I'm saying that right. All right, so what I'm going to do to solve this, I'm going to put, see how that's negative? I'm going to bring it over to the other side by adding it. And see how this is negative? I'm going to bring this to this side by adding it, okay? So this is going to be mc T1, and these are all of water, plus mc T2, and these are all of aluminum. I'll put the numbers in a minute, is equal to mc T2 plus mc T2, right? And these are water, water, and this is aluminum and aluminum, right? And T2 is what I'm looking for. It's the same temperature for everything. Oops, oops, oops. That was supposed to be T1. Okay. Now I'm going to factor out the T2, which is equal to T2 over MC plus MC. Water and water, aluminum and aluminum. Okay. And now I'm going to say, all right, T2 then, I'm going to divide both sides by that mess right there. Okay. So I'm going to go back up. Here's my first side, and that is MCT1 plus MCT1. This is water, water, and water, and aluminum, and aluminum, and aluminum. Is divided by MC plus MC, and that's water, and water, and aluminum, and aluminum. Okay? Now I'm going to fill everything in, and I'm going to do it. I'm going to actually do it in real time, but I am going to change colors in case you can still see what I'm writing, and hopefully that will be okay. So what's the mass of, and we say we were going to circle the waters, right? So what's the mass of the water? It's 105.3. I've been real careful with my units, so I'm not going to write my units in here, okay? And what's my specific heat of the water? It's times 4.18 times in T1 where is T1? 15.4. 15.4. All right, and that's this first term right here, right? I warned you this is going to take a little bit of tenacity. Now my mass of my aluminum is 32.5 times my, I just did that. Now I'm going to do my heat capacity of my aluminum, which is 0.903. 903. You can see this is a times, and that's a decimal. If you get this wrong, it's going to hurt. And T1 is 45.8. 45.8 divided by the mass of the water, which is 105.3, times the heat capacity of the water, the specific heat capacity, 4.18. Now you can't see that. All right, hopefully you got your paper out. I just did those two, and I'm going to do the mass of the aluminum, which is 32.5 times, just did that. Heat capacity is 0.903, 0.903. All right, and I'm going to just do it all at once. All right, so I'm doing it on my calculator, which I can see what everything's going in. I'm going to use parentheses copiously, 105 or liberally, 5.3 times 4.18 times 15.4 plus 32.5 times 0.903 times 45.8 and parenthesis divided by divided by all that mess, and I get 17.300236674. 17.300. There was 3 sig figs used for everything. Well, not that one, I guess, but 3 sig figs used for everything here. I'm going to assume this is 3 sig figs without even going through the game. 17.3 degrees Celsius. And the last thing I'm going to do is I'm going to say, does that make sense? If I have metal at 45 and water at 15, is it possible that they're going to meet in the middle at 17.3? The answer is yes, it is possible. First of all, I have a lot more water. Water has a big heat capacity. I think the most important thing here is that 17 is between them. And if you get a number that's not between 45.8 and 15.4, you know for sure it's wrong. All right, so the answer is 17.3, and we did it through, frankly, solving for T2. The big deal, I think, was right here, though. This was the big deal. That was the trick. Assuming that they're equal, and the rest of it is algebra. Okay, let's do another problem. Let's now think about work. Okay, so we've talked about that already. Work is a force that's applied to a distance. Another way to think of work is it's a change in volume against a constant pressure. So work is minus P delta V. This is sometimes people call this PV work. All right, so work can be defined as, and I'm reading essentially to you off of page 234. That is a change in volume against a constant pressure. So let's look then at a problem. Inflating a balloon requires the inflator to do a pressure volume work in the surroundings. If a balloon is inflated to a volume of if a balloon is inflated to a volume of 1 liter, I'm sorry, from a volume of 1 liter, to a volume of 1.85 liters. I don't think I said that right, but you can see it, okay? The change in volume is what? 1.75 liters, right? Remember now, change is final minus initial, and so indeed it is positive, right? 1.85 minus 0.1 is equal to 1.75 liters, okay? Against a constant external pressure of 1 atmosphere. P is equal to 1 atmosphere. How much work is done? Aha, in joules. So watch this now. Work is equal to minus P delta V is equal to 1.00 atmospheres, 1.75 liters, right? And it's a minus because of that, right? So it's going to be minus 1.75, watch this now, liter atmospheres, okay? Now, that is not a joule. A liter atmosphere is not a joule, right? So what we have to do now is we've got to go to a conversion. I'm going to show you how I convert these, all right? The way that I convert it is I look on the front page of my exam or my quiz, and I look for my R's. And I know, watch this, that 8.314 joules, right, R is equal to 8.314 joules per mole Kelvin, which is also equal to, watch this, 0.08206 liter atmospheres per mole Kelvin, right? So if these two are equal to each other, then I can say, all right, well then it must be that 8.314 joules is equal to 0.08206 liter atmospheres. So I'm going to divide both of them by 0.08, or let's see what I should, yeah, let's divide both of them by 0.08206, 8.314 over 0.08206. That's going to give me joules. That many joules is 1 liter atmosphere, right? This is how I get this conversion. And so I'm going to do that in my calculator. .314 divided by 0.08206 gives you 101.32. So 1 liter atmosphere is equal to 101.32 joules, okay? Okay, so 1.75 times 101.32 times 1.75 gives me 177.3. 177.3 joules. Okay. How much work is done? How much work is done? All right. So really the answer is minus 177.3 or minus 177 joules. That's how much work is done. However, the way that they said it is done, really, I myself would give credit for the magnitude of this. So 177 would be fine, right? Because that's how much work is done. It doesn't say how much work is done by the inflator, right? Well, it sort of does. It sort of says it here. I don't like the way the question is worded. When it says how much work is done, that sounds like an absolute value question to me. And there's the answer, 177 joules.